Previously, we saw the COO format, which stores each non-zero with its row, column, and value. That works, but if there are multiple entries with the same row, we're repeating the row index every time. So the next representation, compressed sparse row, or CSR, fixes this by grouping all non-zeros row by row. So instead of listing the row index for every value, we'll record where each row starts and ends inside an index array. For the first step, we go through the matrix row by row and collect the non-zero values as well as their associated column index. So for the rows 0, 1, 2, and 3, in columns 0, 1, 2, and 3, we collect the row and column values. So for row 0, we collect these non-zero values. And we also collect their column values, which were 0 and 1 respectively for row 0. Now for row 1, there are 3 non-zero values. So we build a column and we extract their values. And these were 0, 2, and 3 respectively. And we do the same for the remaining 2 rows. Now for the key step in compressed sparse row, we build a row pointer array, which is often called a row pointer. In the row pointer, each entry marks the index position in the values array where the new row begins. Given these, we have row 0. And if I concatenate that with row 1, and start building the row pointer array, we see row 1 starts at index value of 0. And row 2 starts at 2. And now we expand to add row 2. And we add row 3. Now let's add entries into our row pointer for the remaining rows. Row 2 starts at entry 5. And row 4 starts at entry 7. The last entry, which is 8, marks the total count of non-zeros. That's how we know when the row ends. So as you could see in compressed sparse row, it maintains the column index and the value index similar to COO. However, it includes a new row pointer. But what happens when we need to add a new non-zero to the matrix? Let's say we add a 1 to row 2, column 0. How can we add this to our compressed sparse row? So when we insert an element, we must place it in the correct position within the row. And we keep the column index sorted. So for us to do this, we must shift all the values after the corresponding spot to the right. And now insert the value for the new non-zero that has been added. So as we can see, it's in row 2. And it has a column value of 0. Oh wait, we're not done yet. Shifting the values to the right cause our entire array to increase in total numbers as well as the row pointers. So every row pointer after the value needs to be incremented by 1. And as such, we get a new compressed sparse row with row pointers 0, 2, 5, 8, and 9. As we can see, this is more expensive than COO, but now we have a more compact format where we could access every element within a row.